Alright, I thought I would try this out just to sort of review the bar graph approach. We're not going to do bar graphs anymore, we're just going to circle the applicable energy. So, a ball has an initial velocity of 3 meters per second, there's no friction, we want to know the highest the ball can roll. So, at the beginning here, they call that VI, we should just be clear that that's U, the initial speed. And here at the top, V is 0, and here H is 0. So labeling things, we don't have any elastic energy. We don't have any gravitational at the bottom, but we do have kinetic. And at the top, we have only gravitational. There's no elastic, kinetic, or dissipated. So keeping it simple, Eg equals Ek equals Eg. And here's an interesting fact. Let's write down the formula, 1/2 mv squared, sorry, that should be Eg at the top, equals mgh. So Eg equals gravitational, the kinetic gets converted into gravitational, and we write down the following formulas. Now notice something, we don't have a mass, and that's totally fine. Times 3 squared equals 1/2 times m times 3 squared equals m times 10 times our unknown h. But look, m cancels on each side when we divide. So we're going to end up getting 9/20 equals h. And when we simplify that, that's going to be 0.45 meters. Now here, it says if the height is only 0.2, what was the amount of energy dissipated? So we'll say Ek, which is what we start with, gets converted to Eg and E dissipated. So Ek gets converted to Eg and E dissipated. Kinetic energy becomes gravitational and dissipated. And we're going to isolate this quantity here. So we'll say 1/2 times m times 3 squared equals m times m times 10 times 0.2. And so we'll end up getting 4.5 m equals 2 times m plus E dissipated. So it turns out the dissipated energy is going to equal 2.5 times the mass of the object, whatever that mass may be. So it's actually kind of good that we solve questions like this. It's not something I would put on a test, but it's definitely a good question for us to consider in practice problems. So here for the conservation of momentum problems, we may go over those in class. However, we need to move on to some new things. So I will post solutions to this, and we can check in on class. We can check in individually on these outside of class if you have trouble with any of the answers. So I'll post PDF solutions, and that'll be the last of the videos I do for the homework.